because I think it's asking you to accept that this is recorded. Okay, awesome. So we started recording. I believe this is share. And let me see something else. It's been a while since speaker options, share display. All right, so these things. What else? Let's try to look for. Just give me a second, guys. Looking for an app here. Not see this. Let me change then. No need. I believe you can see this. Yeah. All right. So we can start finally. And I believe this was the last slide we discussed. It was this one or either this one here. But in any case, yeah, this was the last one. And just to summarize what we did last time. So basically, we started talking about kind of a few concepts that you already knew, which kind of what are the ultimate limit states, service limit states, and we were talking about a little bit about these steel structures, properties, and so on. Yeah, and then we stopped here where we were talking about durability, and the message in this slide was that sometimes we are not able to know many things about design because we are new to it. Yeah. So, for example, I was explaining the case for me personally about this situation, and actually it happened very early, and I want to repeat it here. So, graduated, they asked me to do a design. I did all my strength calculations, stress determination, everything, and then I need to use this U shape like this because here like this, and then some other stuff were going to be kind of attached to this part here, and this was going to be a hinge, practically like this. Yeah. So meaning that this could rotate around this pin here. And it was perfect because I had designed everything, nuts, bolts, connections, everything there. But then this kind of already experienced guy that he was the one who would take all calculations, all comments from engineers, and then do the drawings. So because the philosophy there was that engineers barely did drawings or drew anything related to their designs. So they just focused on creating all, verifying using all the calculations they needed to do, and then sending all those documents to this drafter or drawer, I don't know how to call it, and then this guy would do it. And then this guy said, John, why are you using this U shape like this? I said, well, what's the matter? Because it resists, it is fine, so everything is calculated. It has a beautiful safety factor, so why not? And then he said, well, because this is going to be outside, and then it's going to rain. A lot of leaves are going to just fill out here, and that's going to be a mess. So why don't you, let's say, use it differently? And then we're discussing, arguing about things, and at the end I said, what, okay, this is what I need, so you do it. So what I want to say with this is that these details, they do not standards of basically textbook. They can have certain reference, but the situations where this can happen can be so many and so varied that you are not going to have access to all of them in a textbook or a class. So you have to learn it by making mistakes, or by having a little bit of common sense, or seeing what other people have done, and then you replicate it, done successfully, and then you're replicating it. So this is what we were talking about there. Now, I believe we didn't touch on this, but no, steel is a very sustainable material. We were talking about that because it is the one material that you can just build something with it, destroy that building, and use the here without losing its properties. By the way, one thing that I hate about Teams is that it has a lagging. For example, if I draw here, it takes about 2 seconds to appear on your screen. So that's something that I believe with Zoom doesn't happen, but I had a problem with Zoom, so I will try to fix it. And then this is something that we need to take into account. The beauty of using steel. Yeah. It lasts many years. If it's taken care of properly, any possible corrosion or something that affects the integrity of the steel itself. So another thing we were talking about steels was that you can shape it basically in any shape you want, and that's something that is for us as engineers or consultants, it's a very nice advantage because the limitations are only in our mind. Let's put it that way. Now, have any of you been in these factories where steel is manufactured? You can say yes, no. Like chat, unmute yourself if you want, no problem. I would love to hear you.
No, I haven't.
All right. So she hasn't. And she left. Maybe she clicked some strange button. So steel, and carbon plus other ingredients. And for sure, we have standards to cover what's the perfect composition of those elements there. These pictures, actually, this comes from the place I used to. This picture is from the place when I first started working as an engineer. This is called continuous slab casting. I didn't work directly with the people operating this. This is called continuous slab casting. And what basically happens is that you melt everything. You melt, the iron. You add your additive, everything, and then you put it in some sort of a mold, and that mold, the steel starts solidifying, and it does some sort of big round shape like this. It is a wonderful process. I used to work these platforms here because my office was right next to this part, was something like here. And so this was the day-to-day to see for me how it was done. So after a while, you just lose interest in what's happening here, and then you just worry about your job. But this is continuous slab casting because this strip is called slab, and this height is about 150, 175 millimeters. And this is a continuous strip, basically. But of course, you can't have a continuous strip. You have to cut it. So you have some flame cutters here that they attach to the surface, to the movement of this slab, and then they cut it. And after they have cut, they just push it here. They go to some cooling chambers, and then they just are transferred via crane to another place where they are going to be transported to some other place that we're going to see. But yes, this was kind of a typical. I went to the internet, so I went to show some pictures where I used to work. And then here is what is called hot rolling. That you take this dude and you transport it after days. It's not immediate. Yeah, for our case or this case was not something immediate. It was not a continuous chain of processing or operations. They are stored somewhere in a warehouse or the patio or outside, and then after a while, they ship it to this plant. It was inside of the same area called hot rolling, and what they do is that they reduce the thickness of this slab. Yeah, so they take it, I believe, to 20 to 10 up all the way up to 10 millimeter thick. So imagine that when you squeeze this, so what's going to happen is that the length is going to increase. I hope that you cannot hear the. And then certain thickness, and then this is if you want, you sell this, and then you take it to what is called cold rolling, and then you can make some fine, and then you can do whatever you want with it. Yeah, but this also I worked a lot in this area. I used to work here, so that's why I want to share this picture. So this is where how things are going. And for sure, there are other type of processes where, for example, you take this and then you cold or hot form, for example, the shapes of the profiles we use for beams, columns, and other stuff. I didn't put that one here, but it is basically the same process. Yeah. This is was a wonderful experience in that sense. It's very, let's say, labor intensive. It's something that you have to have a thick skin to work in these type of places. Not because, not only because of the environment it has, but because of the demand and because everything that is subjected to heat, deteriorates faster, and then people have to be on top of it so production doesn't stop. Because if some equipment fails here, it's very difficult to kind of get rid of the whole molting kind of the pot that contains all the hot iron or melted iron that is dripping here. So this is formed. So these were about 200 metric tons of steel or liquid steel, hanging on top of that. Imagine that. So this is where it comes from. One of the formations we were talking about were mechanical properties. And then these are different type of profiles. For example, we have these L shapes, we have T shapes, Z shapes, U shapes, I shapes, H shapes. Yeah. And these come from these type of materials or similar type of materials. And sometimes when you have a big project, we were talking, I believe, I now I'm mixing courses because more or less are related, but the material changes between concrete, timber, and steel, is that, sometimes you're on a big construction, you're going to use a lot of material. For sure, the manufacturer is going to tell you, well, this is the quality of the material, these are the mechanical properties, and so on. I guarantee you that these are, believe me. And then you say, well, you know what, I sure don't believe. So what you say, what you do is that you take a sample and then you make a cut of these materials. And this cut usually have this sort of shape. And what you do with this shape is you make a monoaxial, axial, or uniaxial tensile test, which means that what you're going to do is that you are going to validate that from the sample of material you have there, you can say, what, yes, what was reported as original quality for the steel I'm using here corresponds to it because we validated it using a third party or laboratory or in-house laboratory, depending on the cases. And this is a specimen which is standardized, meaning that these values are completely standardized and people follow it. And how do they extract it? Well, they just cut, if this is the beam or the H, let's use this one. If this is this T beam here, we try to draw it a little bit like this. So what they do is that, yes, they take this part here. Just use a different color. And then they cut this from a piece of steel. And they form that specimen according to these dimensions. And after that, they take it to the uniaxial tensile test to validate at least what are those that we're finding, looking for. We're finding these, try to write it with the same notation here, which is the yield strength and the ultimate strength. Have any of you guys done this kind of tests in your experience, professional life? It would be nice to know if some of you have done it and could comment on that. What did you like about it? Any challenge or drawback? Would be nice if any of you who had experience, have worked with this before. Would be nice to know. The other thing is fatigue resistance. Fatigue covers what is the dynamics of the building. So fatigue, when you guys hear the word fatigue, you have to associate that with movement, motion. And one of the things that we deal here in these courses is that we're considering that these buildings are static, or the elements of the building are static. Equilibrium conditions appear, that's it. However, there might be elements within the building, because remember that we talked about, at least for the concrete part, that there is a resonance, that there could be a vibration in the element. So imagine that you have some right here, you have a beam here, yeah, and then this beam has its permanent load, that the one that we know, like the weight, some walls, material that is not going to be going anywhere. However, we have certain loads that they are going to be kind of variable loads, and they are going to be, as the name says, varying over time. Yeah? Let's call it F1, and then let's call it F2, and let's call it that they varied over time. So we know also that because of this, let me try to kind of to put it as a simply supported beam here, that it might be that a small deformation because of this application of this variable load exists, goes from 0 to a certain maximum value over time. So it's repeating. So if this is the center line of the beam, so it might be possible that that center line is going to change to something like this. Let me see. Yeah. Which is that the deformation, I don't want this one. This deformation delta is going to be between a mean and a maximum. So when we have alternating strains or deformation, it means that we're going to have alternating strains, which means we're going to have alternating stresses. Because remember from our course, I believe strength of material, that is a relation between 5 factors. So the first factor was that if I apply forces to a structure, internally, we're going to create stresses. And those stresses on the material, I'm going to put a big M here, are going to create strains. And strains are going to create, I'm going to like this, deformation. So if I have deformation, it's like going backwards in this linear equation. I have deformation, I'm going to have strains. I have a material present, so there's a physical entity there. So I'm going to have variating stresses there inside of the material. And those variating stresses could lead to a failure due to fatigue of the material. But what is fatigue of materials? Well, fatigue, is like, if we're doing some exercise, some sport, I feel fatigue, it's oh, I cannot do anymore. So it's not quite like that in steels. So fatigue, in the case of steels, what it says is that a metal or steel can fail even though the stress applied to it is smaller compared to the yield strength, here it is, to the yield stress or to the ultimate strength. So let's make an example, or let's take an example. Imagine this steel, the S235. So we know that the yield strength of this steel is 235 megapascals. But let's remember from a table we saw previously that it is 235 megapascals depending on the thickness of the material that we're using. Yeah? So let's keep that in mind. But let's consider, it's 235 megapascals. And also, let's consider the ultimate strength. And actually, we could go to the table I had it. So I'm not, talking nonsense. 360 megapascals is the ultimate strength. Let me go back here. Wait a second. Where am I? Here. 360 megapascals. All right. So what this says is that, okay, so let's remember that these values come from the stress strain curve, something like this. And then we have this nice coordinate reference system like this, stress and strain. And then we have in the middle this curve like this, yeah, where these 2 points are the ones that I'm interested on. And I say, well, you know what? This is Fy and this is Fu, those 2 points. Yeah. Say, well, if the stress applied to the material is in this region here, so there is going to be only lasting deformation. As soon as I remove the stress, that's going to disappear. So no biggie, nothing happened. However, the concept of fatigue says that if you are removing a stress on a steel, and even though the stress is small, something like in this level, let's put it like that. So what's going to happen is that this steel can still fail. So 100 years ago, 150 years ago, German guy called Wöhler devised this curve, and this is called the strain stress life curve, where this is life and cycles to failure. So how many loading, unloading, or passages between mean and maximum are happening, going, and then here what you see is 0.9 of the ultimate tensile strength, meaning that if I would like to make a modeling of the S235 steel here, well, actually, this point here would be 0.9 times 360 megapascals. So how do we read this? It says, well, if, and let's make a clear division here. Any steel, any stress that you impose there on a basis of a cycle, minimum to maximum, maximum to minimum, and so on. Let's imagine that it is here. And let's imagine, well, this is kind of half, so 180 megapascals, which is even less than the yield strength of the material, meaning that you would be happy as an engineer if the stress applied to the steel is way less than the ultimate strength of the material. Yeah. So what it says is that, hey, if you applied a cycling stress of 180 megapascals here, so what's going to happen is that this is going to come here and touch this line. And when it touches this line, it's going to come back here. And this is going to tell you that this steel element part of your structure is going to fail, and let's put a number here, at 10 to the power of 5 cycle. Let me try to write it better. It said better, but it looks ugly. 10 to the power of 5 cycle. So even though I guaranteed that the load was even smaller than the yield strength of material, this element can still fail because of fatigue failure. And this is when we impose or we cycle a load on a steel element, from minimum to maximum. You're just, going from 0 to 10, just, or then from 10 to 0 and so on. So you're just jumping like this. But it could happen that you're just, loading the beam several times and then releasing and stuff. And this is amazing because this is another world. This is another thing. And then you're seeing different areas here. For example, you have this thing that says low cycle fatigue, high cycle fatigue, and then infinite life. So there was a convention that people in 50 years ago agreed, or I believe it was 50 years ago, that they said, if then it's considered that failure is low fatigue failure or low cycle failure. And then if it's between 10 to the power of 3 and 10 to the power of 6 cycles, then it's high cycle fatigue. So what do we mean by 10 to the power of 6 cycles? So 1 million cycles, it is exactly 10 to the power of 6. So then you can do the math about how many times you are cycling this from minimum to maximum to get, in time to get 1 million cycles. Just kind of an example. But then they said, but you know what? We cannot be testing elements, steels for life, because then, when it's going to stop, 10 to the power of 10, 10 to the power of 20. So when if the specimen you are testing, fatigue testing, lasts more than 10 to the power of 6 cycles, it is considered to have infinite life, which means for us, we're going to consider that that's never going to fail. So meaning that there exists a level of stress where you can be cycling a load there, if you keep it in this range, that then you can consider it, you know what, this is safe and this is never going to fail because of fatigue. Okay? And that limit is called endurance limit. Then there is a bunch of things like endurance limit is, you have a laboratory endurance limit, and then you have to model options, and then this is going to be kind of reduced until a certain point that the real endurance limit you're going to be using is this. And then there are other theories that says, well, if you are working with infinite life and you want to know the safety factor in infinite life, there are 4 or 5 failure theories that tells you what's the safety factor of your element member here. It's a beautiful field, I would say, but it's not that attached to a construction or civil engineer. But guys, everything that moves, everything that is subjected to cycling loading, is going to suffer via fatigue. And let's say that the preferred design method is fatigue. Car parts, cars, airplanes, space shuttles, boats, anything that you see move, design based on fatigue. For our case, there's a specific section of the Eurocode 3 which deals with steel structure. Okay, approach this. So it's not leaving, let's say, unarmed in this case. Do you guys have any questions so far? Because this is an interesting topic, but this is something that is heavy. Yeah. Let's see. There's a question in the chat. Search the chat. So somebody you asked about what about full steps in the building? Is it a small load? What do you think? What You can unmute yourself if you want. It's better if you can. Actually, about that question, I don't know if you have seen this. I'm going to try to find a, just give me a second. So, I've seen, I've seen it in Russia, actually. I've visited Russia, well, in the past, was about 3 times. And I'm going to show you. Just looking for a picture. Not mine, just for internet, but I know what to look for. So let me see if I can. Here. Yeah, this one. You can see it. So remember was in St. Petersburg. Yeah, well, 3 times. Well, I've been more times in Russia than 3 times. I've been quite a lot of time in the past when I was living in La Perranda because it was very, very easy to just cross the border from La Perranda. Was about 20, 30 kilometers. That's it, less than that. And we used to go to the border to put gasoline because the gasoline price was 1/3 or what was in Finland. So you could see in the evening there were even cameras in the customs, in the border. The queue is not that bad. So you could see, cars of Finnish cars just queuing to go to the gas station just next to the border, put some gasoline, buy cigarettes, smoke, and then come back in a couple of hours. So I visited Russia many times. I would have done this smartly and how it was worn out and stuff. So I just wanted to share. So it's not related to fatigue or anything, but in footsteps, in staircases, maybe there are other more concerning situations than fatigue itself. For sure, if you are trying to design any fixations or stuff, you need to make sure that that's according to standards. But I just brought this out because in those footsteps, like that, it happens. And then for sure, if you're working on a floor, something like that is not going to be like that. But this amazed me at the time. Yeah. Anyway, or maybe unrelated, but nice comment. Yeah. So that was one of the things we were talking about. That uh, still, if it's not going to fail because of any abrupt failure, such as do you put a huge load because of, and then it just kind of exceeded the ultimate strength of the material, or it's not going to fail because of fatigue, then one of the biggest, let's say, enemies of steel is corrosion. So that's why steel parts are covered in some specific products to avoid corrosion or to increase the resistance against whether it's going to be exposed. And so because what happens with corrosion is that when corrosion happens of strength, and let's look at it from the point of view of fatigue, when corrosion happens, then strength of the material reduces. And secondly, when we talk about fatigue, when we talk corrosion, we were talking about the endurance limit. One of the things to bring the laboratory test of an ideal specimen endurance limit to a real endurance limit is by using fatigue modifying factors. They're called marine factors. Let me write it down here. Here, marine factors. One of the marine factors I believe is in the miscellaneous factors or something like that, where it covers corrosion. And then when you are in the presence of possibility of a crack appearing on the steel, increases tremendously, which means that the material can fail more rapidly. So that's why we need to protect steel against corrosion. There are other type of materials that they are anti-corrosive, let's call it like that, by default, like stainless steels, maybe you're working with aluminum, but it's not that they have a protection against corrosion, it's that they are already corroded. Actually, stainless steel, what you call stainless steel, it has a layer of oxide on top of it, and meaning that it's corroded already. But let's call it a positive corrosion. And that's why it is fine to work for us, or it works for us very, very nicely, because it's already, hey, don't worry about corrosion because I'm already corroded basically. But it is because it has a layer of oxide, that is formed by this. So that's what's happening there. But yeah, this is a very important topic that it is something that we need to take care of. And then other thing that happens is that, hey, you say, hey, yeah, the uniaxial tension test is fine, but that's not going to guarantee that it's going to fail in a different way. So that's why that you're going to find certain. I'm a little bit kind of my throat is a bit aching, but I'm trying to. So there's another type of tests that are kind of designed to tell you, hey, is this going to fail by a rapid, it's going to break because of a rapid loading. So imagine that you have an element and that you suddenly applied a load to it, kind of, you have an element, let's keep the beam, and then suddenly, boom, a force appear here. So is this going to fail in brittle way when we talk before it breaks? Let's remember that when we talk about steels, we have uh, ductile steels, and then we have brittle steels. Brittle. This is the word I'm trying to say. So ductile steels, the ones that we use actually for our constructions, are ductile, meaning that before they break, they are going to deform tremendously, and then they're going to break. So firms, you see a deformation, and then it breaks. However, there could be some sort of brittle, let's say, failure due to rapid loading, and there exists a test called the Charpy test. And Charpy test, let me check if I can bring a figure of it. It's a very interesting figure. Of the machine. Yes, this one might do the job. This one. Here it is. So what happens here is that you put a specimen. This is your specimen here. Let me just use the laser. This is your specimen. It has a notch, and all of this is calibrated and calculated. So you put here, and you take this. This is a big, heavy weight. Yeah, hammer they call it. Yeah? And then you put it to a position, and when you put it in the position, you just well, first of all, you don't have any specimen here, so you don't put it. So you take it to a certain angle or position. It could be 90 degrees or a specified angle depending on the machine. And once you have the initial position, the hammer, let's call this the initial position, you put the scale to 0 here. And then you release the hammer, and this is going to come like this, and then it's going to reach certain level here. And then this is going to have certain, well, this might not even move or anything. It's just going to be there. So just guarantee it's going to be 0. Then you put it back in the initial position. You put the specimen back here like this, and this means that this is what the hammer is going. This is the hammer here, and then you release it, and when it hits the specimen, it's going to break it hopefully. Then that impact is going to make this dial go to a certain level, and this level is going to tell you kind of that those guys have devised a scale that tells you, hey, if the scale gives you this, then the toughness of this is going to be this. And basically what they are measuring is how fast this can fail in a brittle way when a sudden load is applied to it. This is a Charpy test that is known. Also, for sure, there are standardized versions of it. But let's look at something, because I believe we're going to have time for something interesting. So this is an I-beam, roll I-beam. Well, this is a sort of not an I-beam, but it's a typical profile that we're going to see, and you have seen for sure, those of you who are experienced. So, for example, if we call this, let's call it an I-beam, even though it's not a perfect I-beam, because an I-beam is some sort of, let's say, tapered or inclined here. Yeah, and flange here or flanges here. Then you have the web here. You have the dimensions of the web, for example, thickness of the web, thickness of the flange, which is TF here. Then you have depth between fillets. So this is the fillet here. Then you have the depth of section. And remember that we talked that sometimes you're going to find it as height of this section, but typically you're going to find it as depth of section and then width of section. And for sure, the root radius. These are the typical values that manufacturers are going to give you. And let me show you, for example, from one of the maybe manufacturers. Yeah, this is a perfect one because I believe we're going to use it. Like this. So you see, you have the width, the depth, you have the thickness of the web here. I just see that you're not seeing this. Thickness of the web, thickness of the flange, root radius, width, depth. For sure, one of the dimensions is missing is the depth between fillets here. Probably you can calculate it by using the root radius and then the total depth. But this is the one that we need to keep at hand because we're going to use. Then you have different shapes that we could use. Now we're talking, also we saw it. We have the IH tube, square tube, round tube, C channel or U channel, LT, some other shapes that are using composite together with concrete. But one of the most typical we're going to use are going to be the I and H sections. Now this is one of the ones that we're going to do exercises with. Well, I'm not going to exclude, for example, angles or these ones because they propose an interesting characteristic, which is something called the shear center that we're going to talk at some point. And here, for example, from the standards, I believe it's this one, this EN 134 says, okay, if you're going to buy this kind of stuff, what are the tolerances you can accept? And for sure, when this material is manufactured, it can happen that this dimension is different than than the one that it should be. I'm just going to tell you, for example, is the depth is less than 180 millimeters, then you can have a plus minus 3 millimeters tolerances. So what does that mean? So it means that if this friend here is 100 millimeters H, then you could expect from the supplier of this material that this dimension could be between 97 millimeters and 103 millimeters, according to this standard. And it would be okay. Yeah. So is that a problem? It might be a problem, because you need to consider that even though we use precise figures to design steel structures, this tolerance here is a lot. Because you can find two elements, two beams, or two beams that one has 97 as depth, and then you can have the other one that has 103 millimeters as depth, and then what you're going to find is that those two are going to be something like, let's change this. Something like this. Oh, this is ugly, but I hope that it works. With a difference of 6 millimeters here. Change this. Oh, it's not going anywhere. Small. It is 6 millimeters. So these are some things you need to take into account in the tolerances of your design. For example, you also have the inclination of the flange, how deviated it could be with respect to the web. This one here, could be deviated in that way or it could be deviated in this way. So the thing is that everything has to be within tolerances, and then you have to be aware that this can happen. Also, you bought a nice 6 meters profile for your design and is bent like this. So how much is enough to say, yes, well, I would accept it, or no, I will not accept it? Well, you see that they have this value here. I say, well, depending on the section height or on the depth depending on this, it could be 10%, 50%, or 30% of the length, meaning that the smaller, the shortest the depth, the more variation it as a tolerance, let's say, accepts. Let's take an example. For example, let's say, for example, that this is 200, just to make a number here and say, you know what, I want to know physically what does it mean. So we have this, and let's imagine that this is at 200 millimeters depth. So if it's 200 millimeters, it means that it's going to be in this region here, which means that this is only going to accept 50% of this value as tolerance for even the how to call it, the straightness with respect to section. So how much is that? So if I make a quick calculation of this, it's going to be 200 times 0.15, 30 millimeters. Imagine that. So this could be 30 millimeters, like this, and oh, and this 30 millimeters. Now, question to you guys: when you first saw, for example, if you buy something and this comes like this, bent already, so what was the criteria for you to tell, the vendor and say, no, I'm not going to accept this because this is our spec or something? But actually, initially you would like to have everything that is straight. Yeah. What's the problem with having these? Straight out, you have to pull this down kind of in this way to make it down, and then you're going to use a deformation on the original shape of the beam. So even though it is already deformed, or let's say bent, so the fact that you're going to pull this beam to this in this direction, so you can get rid of these 30 millimeters, you are going to deform the original, let's say, configuration of the beam. And then if you deform that, you're going to use a strain. Remember this: you have material, and then the strain is going to create due to the material stress, which means that you're going to have an element where not only actions on the element are going to be causing stresses, but your let's say your action of straightening this out is, you know what, with all the factors we have considered, if it's following this rule, we are okay. No problem. You don't need to do anything extra. Any questions, guys? And with this one, what I want to just mention, this is kind of the same sections that we've seen later, is that according to the European standards, remember that we have inertia axis. So we have, if we try to draw the section in a three-dimensional axis, such as this, for example, where we have, in this case, is y, this is z, and then the one pointing towards the screen, actually, it's this. This is kind of the arrow of this element here. This is x. So in tables from European manufacturers, what you're going to find is that y is always going to, let's say, represent the strong axis. I believe that's the word we can use there. The strong axis. Z is going to represent the weak axis, and X is going to represent the longitudinal axis. So just to be clear, so we need to keep that present, that always Y is going to be the strong axis. What do I mean with the strong axis? So let's take, for example, this beam here. If I applied a load here in this direction, F1, let's call it. So it is going to require certain amount of load to create certain amount of bending moment about the y-axis. Now, if I apply, and this is going to create a, let's say, a moment, or a bending stress. But then if I applied another force, or the same force, but in this direction here, this is going to create a bending stress around the ZZ axis. So for the same value of force, the stress created around the ZZ axis is going to be way larger. Well, not exaggerate, it's going to be larger for this case than the stress created in the YY axis because of the geometry of the section. So that's why this is called the strong axis and this is the weak axis, because if you want to support the most amount of force, then you better use it in this position like this. To mean you apply the force so that the bending occurs around the YY axis. Yeah. And this is a very good representation because you now know that, if you want to take the maximum out of a beam, so use it in the way that, the bending is going to be around the strong axis, which is the YY axis. Same happens with this one. Same happens with this one, and you can do the calculations here. Same happens with this one. So meaning that it's easier to bend beam if you apply the force here than if you apply the force here. That's what it said. Any question, guys? Then let's jump to another thing. So, okay, we have talked about, and we have a lot of things to talk about, but let's try to start doing something practical. Stop sharing, and I'm going to kind of jump to this one here. Share content, screen, window. If you can see it. So let's see what happens when we try to say, okay, John, we want to already do something. And let's imagine that we have, I'm going to look for it. Maybe this one. Well, yeah, this could work. So one of the things that is characteristic is that, well, maybe this is not the best one. I hope that you could see my annotate screen. So can this, doesn't show anything. So try to follow with the small pointer of the mouse. So I mentioned that there is one of these beams here. I said, well, you know what? We want to calculate one of these ones. Yeah, one beam here. Usually, what happens or what you're going to find is that most of these cases is that the beam is, again, most of the times only affected by a uniform load, like this one, red on the top here. So you have in blue, you have the beam, and then you have related to floor, walls, say the partitions, equipment, but it could be like this. Yeah? Let's remove this. And previously, this is something we discussed. So, well, you're going to have permanent actions, and you're going to have what I call this. Actually, I cannot see this chat here. There it is. There it is. It could be, the floor, I was saying walls, ceiling services, something like that. Yeah. And here, then that load is divided. Well, you have your permanent actions. Remember that, when we talk about your codes, whatever loads, moments, or whatever we are talking about, we're calling actions. What is imposed on the element. And then we have variable actions, for example, people moving, some equipment that is going to be, shifting from one side to the other. But then you can say, the variable actions are these. And here I don't have any accidental actions such as, any other thing, or wind is not included here, or any other thing. So very simple. No, but we have the values for the permanent actions and then for the variable actions. And also, by the way, this example is not going to be, we are not going to be able to cover it during the remaining time, but we'll continue it. And then we have the beam length, which is 8 meters, and then we have the width of the tributary area. And let's remember what the tributary area is. I hope that you do. I'm going to try to draw it apart, so it's better to bring. So I'm going to draw just wait for me, I'm going to draw the beam. Because I cannot draw there. And this definitely Teams is killing me. Just a second. All right, and one more second. And let's copy this. Oh, there it is. So if this blue is the beam, then the tributary area is that, that we have beams, stacked one next to the other, and then we have a floor on top of several beams. So how much of the floor is, let's say, standing on top of the beam, or how much of the beam is taking from the whole floor? Well, the tributary area, there are ways to do it, but basically the simplest one is to imagine a rectangle here, and if I have another beam on the side, then you're going to know that that's going to be the tributary area. And actually, I could do this. Something like this. where kind of the next beam is here. So you split here, imagine this by half, and then you say, well, this portion of floor is no, this beam is taking care of this portion of floor. That's why no, a width of the tributary area and then beam length. So after having that, we know that these are, as the K shows here in these values, we know that these are one type of value. Remember that in design, we have design values, we have, oh goodness, representative values, and then we have characteristic values. So when it's given like this, with a K, is in the slides, these are characteristic values, but we don't use characteristic values right away. So we need to modify them to convert them into design values. And we do that by using something called, let's say, a specific word for that is partial factors. Yeah. So for example, let's try to write here. And in the design process, we also talked that we could verify our design by using the ultimate limit strength, limit state, and the service visibility limit state. And these are called kind of S, and this one is SLS. And we said that ultimate limit state is to guarantee that that thing is not going to break, it's not going to collapse. And then the serviceability limit state is going to guarantee that it's going to be comfortable for the people and everything that is going to be using the building, people, machine, whatever. Kind of the deformations are going to be kept to a limit, vibrations are going to be kept to a limit, and so on. So the first thing we're going to do is, well, let's try to find out, because the test for this is, let's find out the beam, the profile that could hold these actions under these circumstances, meaning that it's not going to break, and that the formations are going to have are within the limits. Yeah? So for that case, well, we say, well, you know what? Yeah, we cannot use straight away the characteristic values, but we need to use the partial factors for actions. Yeah, and then we say, you use this. I hope that you remember this. Not use partial factors for example permanent actions, and we're going to call that gamma. Where are you, gamma? Here it is. G. And subtracted from your old zero, the value typically is this much. So meaning that this is we're going to have to combine it, but this is a sort of a multiplier of the action. So you say, even though this is the action, I'm going to, to just to cover my back and say a little bit more. Yeah? And then you have the partial factor for variable load action. And that also is going to have a designation, and we're going to call it, well, you know what, that's going to be gamma Q. And that's going to be, for our case, equal to 1.5. That's it. Awesome. But additionally, even though it seems a little bit kind of counterintuitive, is that you say, yeah, but here you say that you're not sure about the value, but then you are increasing all the values just cover back. But the seller say, yeah, but you should increase that much. So we need to use a reduction action. So it is, let's say, you are not over designing your stuff. And that's called reduction. Actually, it's called reduction factor. And that reduction factor, it is expressed by the letter Z. Where is C? Psi. And that's going to be equal to 0.95. Now that I have my partial factors, and we're going to talk soon about this again. So we work with what we have to say, okay, how do I combine these loads? Well, what you're going to do is that you're going to say, and let's call it like action combination, just give a name. And it's going to be a multiplication of some of several things. So first, you're going to say that, and this is going to be expressed in that the reduction factor times the permanent load partial factor times this dude plus this friend plus this friend. I have a mistake here. This is times. There it is. So if you see this equation here, you see that this first part tells you how to deal with permanent actions, and this part tells you how to deal with variable actions. This is called the partial factor method. You know that I have said a lot that we engineers like to apply safety factors. Safety factor because we are uncertain about what's happening in reality. So we say that if a load is 100 kilonewtons, we said, I want to be sure. I'm not sure about what's happening inside. So let's assume that it's 120 kilonewtons. So we increase it by 20%. Yeah. But when you have actions of different nature, like permanent actions or variable actions or accidental actions, applying a sole and only safety factor to all three, it carries a lot of, let's say, over design process. So the partial factor method, what it does is say, okay, let's divide the actions by nature, permanent or variable, and let's apply a factor to each one of the actions per nature. Yeah. So that's why you have here, for example, in these first three, these two, this is the factor modifying the permanent actions, and here this is the factor modifying the variable actions. Yeah. And again, permanent actions are those that they don't change over time, such as the self weight of the structure, any material or walls or partitions that are going to be there, you're not going to move them. Yeah. Variable actions, there are some loads that they can be there and vary there over time. Yeah? And those are the estimations you're going to have. Like people walking, for example, a variable action is people walking on a floor. So if you have a floor where 200 people work, so you're going to have 200 people, then you're going to have 150, then you're going to have zero because everybody went home, and so on. So that's a variable action. Machinery that is going to be transiting, forklifts or vehicles or whatever. So that's what we have there. Yeah. So that's why. But then now, okay, these are the combination of actions. So tell me what the design force that I need to consider, because this is a uniformly distributed force applied on the beam. So what's the design force? The design distributed force. So the design distributed force. Beautiful. Well, the design distributed force is going to be the combination of actions, which is in kilonewtons per square meter. But if I take this combination of actions and multiply it by the width of the tributary area, then I'm going to transform this force per surface into a force per length, which is going to give me the distributed load. Then I'm going to say, well, you know what? The design distributed load is going to be the multiplication of this friend here and this friend here, which means that, hey, you know what? That distributed force is going to be 57 kilonewtons, 57.4 kilonewtons per meter. So here I could be able to write 57.4 kilonewtons per meter. Yeah? So no big deal. Nothing we have done so far that is amazing. It's just multiplying things. All of this is extracted from the standards. Yeah. All of this is found there. Do you guys have a question? All right. So then, thank you, Sumaya. So then, yeah, we have a beam which is fully restrained beam. When I say fully restrained beam, it is that this is not pivoting anywhere. This also is not pivoting anywhere. So it's kind of it is as fixed as it can be. So, of course, when you were in presence of this, one of the things you did in your courses was to draw the shear force and bending moment diagram, because you knew that, well, we now know, or we can know that with the moment, the value of the maximum moment appearing here, then you can have the maximum bending stress, and then with the maximum bending stress, you can find what would be the geometry of the beam that can withstand that, let's say, moment. So one of the next things to do, I believe I will do it right away here, is to calculate, okay, tell me what is the design moment and what is the design shear force. So moment and design shear force, like that. It took me before the next line to fix this, the template. Yeah. So this is a typical beam construction. And we know that the maximum shear moment, bending moment is going to be located in the middle of the beam. And that's a formula that many people know. But, well, let's write it here. So the standard here is going to be that, okay, the maximum bending moment, and look at this beautifulness. We're using the strongest axis as per our discussion before. Yeah? It's going to be equal to the design force times the length of the beam, which is this 8 meters to the power of 2, divided by 8. There it is. This is the design bending moment, and actually this friend is like it. The design bending moment around because this is the one that I want to get around the strongest axis. Remember, strongest axis and weakest axis. Now, E, remember, because actions on structures create effects, and those effects are the ones that are going to be compared with the resistance of the material. So that's why it's called here. Tell me the moment around the strongest axis, or the effect moment, the design effect moment around the y-axis. This is what it's telling you. It's saying, well, for this case, my friend, in this beautiful case, is going to be 459 kilonewtons per meter. Yeah, awesome. Now, in this case, okay, we know that the maximum shear bending moment is in the center, but we also know that the maximum shear force, and this is a very typical case, is going to be at the ends. Yeah, and the value, and actually, let me put it like this: bending moment is this, and shear force maximum is going to be, again, it is a formula also. Then, well, it's going to be the effect, because what we're saying is that, hey, make a cut where the maximums are happening. Remember that those are internal forces. Internal forces are what we call effects in this case. Yeah? And that's going to be equal, it is a table also, that's going to be equal to, where we see the force times the length divided by 2. And there we go, we have 229.6 kilonewtons. Yeah? We're going to stop soon, but the next thing I want to highlight is, okay, I know I need to select a geometry and a material that can withstand this bending moment and this shear force, because we need to verify that it's not going to fail either by this or by this. So standard tells me that I need to use a partial factor for resistance. If I use a partial factor for permanent actions, then I need to use a partial factor for resistance. So I'm going to use here partial factor for resistance, material resistance. And end, here it is. And that's basically depending on how this is working, if it's bending, compression, or if it's in as a column in buckling, or is another effect. There are going to be at least 3 different partial factors, and this is going to be equal to, again, gamma m0, and this is going to be equal to 1. Remember that there are factors that are left to 1 that you would say, why would you leave a factor as 1 if it doesn't modify, the value, the other value it is multiplying or something? Well, because it could change in the future. Yeah? So having this, we're going to stop here, but the next step would be that we're going to find out what's the section we would need to use and how to do it. Okay? So let's make let's stop here. And for those who are going to join in 30 minutes, I'll see you again. See you again. Yeah. Any questions?